In this video series, we're going to be taking a look at numerical methods to where we can start approximating the roots to functions. And the methods we're going to be used are going to be called bracketing methods. So, um, first of all, let me explain what a root is and then explain what a bracketing method is versus something called an open method. A root of a function is just going to essentially be where that function is equal to zero. Okay, so it's a way to solve an equation, right? Bracketing methods mean that we essentially have an interval where we think that the solution is going to lie. And then what we do is we use an algorithm to kind of hone in or to improve that bracket each time until we get to a certain error or something of that nature. Right. Now, an open method, which we're going to look at in the next video series, is going to have a singular guess. And then what we try to do is we try to hone in on what the solution is going to be. So here's what we're going to say a bracketing method. So let's say we have a zero right here of a continuous function, right? Let's call this value right here f at xl, in other words, the lower bound. Okay, so we have this interval xl comma xu, which is the upper bound. So this is going to be our f at xl. And up here, if this is xu, which is the upper bound of our interval, this is going to be f at x sub u. And so what we're going to do is we're going to try to continuously move xu and xl or xl, depending upon what our algorithm suggests, and we're going to try to move in. Okay, so we might move in from this side, we might move in from this side, and ultimately we try to guess what the solution is. Okay, so that's what a bracketing method in its most essential sort of definition might be. All right. Now, most of the time we have some sort of increment size. Okay, so we have a move from here to here to here to here. We have a partition. All right, and we're going to see that in a few moments with our first sort of bracketing method, which is going to be the incremental method. All right. So, three methods we're going to be looking at in this section is the incremental method, the incremental search or the incremental method, the bisector method, and then the false position. Okay, so let's start with this incremental search. And what I'm going to do is I'm going to kind of explain what that is. And then in the next video, what I'll do is I'll code the incremental search for you using MATLAB and we'll explore. So let me go ahead and try to geometrically explain for you what it is. Okay, so once again, we have an XL, we have an XU. And this is going to be our value up here. Let's call that fx sub u. And let's call this down here, let's call this fx sub l. And what I want you to notice is that fx sub u is greater than 0. Okay, it's above the x-axis. And this value is less than 0. So if I was to multiply those fxl times fxu, that should be less than 0 because you have a negative value times a positive value. Right? And what we're going to do is we're going to continuously move x sub l. Okay, so let's just move x sub l up to here. Okay, so I'm going to call this f x sub l plus some sort of step size h, where h is going to be the distance. So this is going to be xl plus h. All right, and then I can keep doing that. I can keep moving it along. Okay. And of course, I never want to move past the upper bound. Okay. I mean, I could keep doing that forever. But once I get here, if I were to ever reach that, that means I just missed something in my interval. But I want you to notice that these two values are bracketing. Okay. But also notice that if I went one more step up above those two values, so if we got to these two values, whatever these two values might be on the x-axis, so something like here and here, all right, then we know the zeros lie somewhere in there. But let's say for some reason our algorithm goes one more increment past that and we get here, okay? What happens is if I multiply these two values together, a positive times a positive, that means we end up getting a positive value. And that's how we know to stop our algorithm, right? So we're just going to keep repeating this algorithm. So we're going to multiply FL times f of xl times f of xu. We're going to multiply those. And if it's still less than 0, then we just move up. And then if it's less than 0, we move up. And if it's less than 0, we move up. And then if it's less than 0, we move up until finally we get something greater than 0. Right? If that's the case, then the solution must lie somewhere on this interval. Okay, so that's what the incremental search method is. Now, the algorithm for that is actually fairly easy. Okay, it's not going to take us too long to code this in the next video. All right, but essentially the incremental search says that if XL is the lower guess and XU is the initial upper level guess for this, then this is going to be our interval. And so we can say that FXL and FU have opposite signs. There's at least one root in the interval. Okay, and so what we're going to do is first we're going to graph the function, make sure it's continuous, and then we're going to figure out what the interval might be where the suspected zero lies. Then what we're going to do is we're going to estimate XL and XU, and then we're going to try to figure out a step size. Okay, now usually you don't want your step size to be too small, but the smaller you are too big or too small, but the smaller you make that step size, the longer your algorithm is going to run. It also means that you're going to get more accurate. Okay, so you're trading off accuracy versus efficiency. Most of the time, you could use like 0.05 or 0.005, and that's a pretty good step size. Okay? And what you're going to do is you're going to multiply f of xl by fxu. All right. If for some reason it's less than 0, then all you're going to do is just replace xl and let that equal xl plus h. Okay, so in other words, you're just moving right up the chain. Okay, so this is fxl plus h, and then another fxl plus h, and another fxl plus h, until finally we get to a point where we multiply those, okay, and the 0 lies somewhere on the interval. All right, now what we can do is we could just take the average of those two values, and the average is going to be approximately the root for the solution. Okay. All right, so now if for some reason, if this is never greater than 0, then we might have made an error when we selected down, so we probably have to select something different. Okay. All right, so our next video, what we're going to do is I'm just going to code this for you. Okay, so I'm just going to code and I'll show you an example of this, but this is the example that we're going to use. Okay, so this is our function and our step size. So we're going to graph it in the next video. We're going to get a lower bound and an upper bound, and then we're just going to see how accurate this can be.